Hello everyone, welcome back to my YouTube channel. In this week video, we shall discuss on questions that covers chapter 6. So altogether we have 8 different questions and let's start with the first one. Question number 1. An unknown gas diffuses 0.25 times as fast as helium gas. Determine the molar mass of the unknown gas. In order for us to answer this question, we can use the Gram's law. According to the Gram's law, the velocity RMS for B divided by the velocity RMS for A is equivalent to the square root of molecular weight of A divided by the molecular weight of B. From the information given to us in the question, we know that we have helium gas and also the unknown gas, whereby the unknown gas shall diffuse 0.25 times as fast as the helium gas. Alright, so we are going to consider that the velocity for helium is equivalent to 1 and 0.25 times as fast means that we are going to use 0.25 as is for the unknown gas. So here you should put 1. So now we are going to look upon the molecular weight of, so your Ma shall be the helium and the M unknown. Right, so what we are going to do now is we are going to refer to our periodic table. Alright, so from the periodic table, we need to look upon the helium. So the helium, so molecular weight is equivalent to 4. So we're going to write 4 here. And then the unknown is equivalent to 0.25. So because we have square root over here, so we're just going to do to the power of 2 for both sides. So what we are going to get is 4 divided by the molecular weight of the unknown is equivalent to 0.25 square. Hence, what you will get is the molecular weight of the unknown times 6.25 times 10 to the power of negative 2 is equivalent to 4. So your molecular weight for the unknown is 4 divided by 6.25 times 10 to the power of negative 2. So you will get your molecular weight for your unknown is equivalent to 6.4 times 10 to the power of 1, which is equivalent to 64 gram per mole. So this is the final answer for the first question. Question number 2. A 3-liter sample of helium was placed in a container fitted with a porous membrane. Half of the helium effused through the membrane in 25 hours. A 3-liter sample of oxygen was placed in an identical container. Determine the duration of half of the oxygen to effuse through the membrane. From the question, it is stated that half of the helium effused in 25 hours. So the total number of the total volume of helium that is available is actually 3 liter. So half of it means that 3 divided by 2, so you will get 1.5 liter. So from here, since we have time and we have the volume, so we can find the rate. So rate is equivalent to the volume, which is 1.5 liter, divided by the time, which is 25 hours. So you should get 0.0600 liter per hour. So this is what we call the rate for this helium to effuse. Now in the question it states that the oxygen is being placed in an identical container and you were asked to calculate the duration for half of the oxygen to effuse through the membrane. So what we are going to do now is we are going to use the Gram's law again. So whereby the Gram's law states that rate B divided by rate A is equivalent to the square root of the molecular weight of A divided by molecular weight of B. Right? So we already know what is rate A, which is helium. So the rate for helium is equivalent to, so now we're going to find the rate B. So rate of helium is 0.06, is equivalent to the molecular weight of helium divided by the molecular weight for oxygen gas. So for this one, we are going to look upon our periodic table. Alright, so from the periodic table, we are going to look upon helium. So helium and also oxygen, so that we can get the RMM for these two elements. So alright, from here we will get rate B is divided by 0.06 is equivalent to square root of the molecular weight for helium, which is 4, divided by the molecular weight for oxygen is 15.99994. So 15.9994, you need 2 times 2 because it's an oxygen gas. So oxygen gas, you have 2 here, so you need 2 times 2. Therefore, your rate B is over 0.06 is equivalent to the square root of 4 divided by 3.1999 times 10 to the power of 1. Therefore, rate B divided by 0.06 is equivalent to 0.3536. Therefore, we can write rate B is equivalent to 0.3536 times 0.06. Therefore, you will get 2.1216 times 10 to the power of negative 2. Alright, so this calculation shows the rate when half of the oxygen is being effused through the membrane. So in the question, you were asked to determine the duration. So when you have the rate means the volume over the time is the rate. So you were given the rate, you have calculated the rate, and you know that half of the volume is 1.5. So duration is equivalent to your rate, which is 2.1213 times 10 to the power of negative 2. Therefore, your duration is equivalent to 1.5 divided by 2.1213 times 10 to the power of negative 2. Therefore, you will get 7.0711 times 10 to the power of 1 hours. Or you may want to write it as 70.711 hours. So this is the final answer for the second question. Let's move on to question number 3. A carbon dioxide molecules travel at 45.0 mole per second at a certain temperature. At the same temperature, find the velocity of oxygen molecule. From the question, you were given the velocity of carbon dioxide and you were asked to find the velocity of oxygen molecule. So what we are going to use is we are going to use the formula for the Gram's law again. So from the Gram's law, we know that the velocity RMS for B divided by velocity RMS for A is equivalent to the square root of the molecular weight of A divided by molecular weight for B. So now we are going to talk about carbon dioxide and also oxygen gas, whereby we know the velocity of the carbon dioxide. We are going to put it as A. So velocity RMS for B divided by 45 is equivalent to the square root of the carbon dioxide, molecular weight for carbon dioxide, divided by molecular weight for oxygen. So the same drill, we are going to look upon the relative molar mass. So for carbon dioxide, we are going to look at carbon and oxygen, and for oxygen molecule, definitely we are going to look upon the oxygen. Alright, so from the calculation, we find that VRMSB over 45 is equivalent to 1.1726. Therefore, we can calculate the VRMS for B, which is for the oxygen molecule, is equivalent to 1.1726 times 45. So you should get 5.2769 times 10 to the power of 1. So what is the unit? Should be the same, which is mole per second. So this is the final answer for the third question. Question number 4. What is the rate of effusion of gas that have molar mass twice of that gas which effuses at the rate of 3.62 mole per minute? Alright, so this is a rather straightforward question where we just need to use the Graham's law. So in Graham's law, we have rate B divided by rate A is equivalent to the square root of molecular weight of A divided by molecular weight of B. In this case, we have two different gases which are both unknown, only that you know that the molar mass of one is twice as much as the other one. Alright, so what we can do now is we write the rate of B divided by the rate of A, which is 3.62 given in the question, is supposedly the molecular weight of A is what we consider as X or 1x, and the other one is twice as much, so 2x. Right? So from here we can slash this out, so you will get rate B over 3.62 is equivalent to square root of 0.5. Therefore, we are going to do to the power of 2 for both sides. So you will get rate B over 3.62 to the power of 2 is equivalent to 0.5. Therefore, we can have your rate B square is equivalent to 0.5 times 1.3104 times 10 to the power of 1. Therefore, your rate B is equivalent to the square root of 0.5 times 1.3104 times 10 to the power of 1. Therefore, you should get 2.5597. So the unit shall be mole per minute. So this is the final answer for the fourth question. Question number 5. 2 moles of helium gas are in a tank at 25 degrees Celsius. Determine the root mean square RMS speed of the atom. So to answer this question, you should use the formula VRMS is equivalent to the square root of 3RT divided by the molecular weight. So before we proceed with the calculation, I would like you to look upon the value of your RMM and also your gas constant. The usual gas constant that we use is equivalent to 8.3145 joule per Kelvin per mole, right? And then when you compare it with your molecular weight, so molecular weight is equivalent to gram per mole, right? So for the mole is okay, it's comparable, but then you have gram here and you have joule around here. So how are you going to know that you should use gram or you should use kilogram instead? So what we are going to do now is we are going to convert this joule into other unit. So bear in mind that joule, the SI unit for energy, which is joule, is also equivalent to kilogram meter square per second, right? So this one. So what we are going to do now is we're going to merge these things together. So your gas constant gonna be 8.3145. So the joule is kilogram meter square per second. And then we have Kelvin to the power of 1, the temperature, and mole to the power of 1. So you need to make sure that when you do your calculation, the mass should be in kilogram, and then the temperature should be in Kelvin, and the mole you will get from the molecular weight. Alright, now we are going to plug in the value. So we will have the VRMS is equivalent to the square root of 3, and your R is 8.3145 kilogram meter square per second per Kelvin per mole. And then your temperature is 25 degrees Celsius, so 25 plus 273, which is the conversion to Kelvin, divided by the molecular weight of helium. So molecular weight of helium is 4 gram per mole. So this gram you need to convert to kilograms, so you need to divide by 1000. So basically what you're going to get is 3 times 8.3145 kilogram meter square per second per Kelvin per mole times the temperature is 298, so you need to divide by 0.004 kilogram per mole. So what you're going to do now is you're going to slash out all the things that we can slash out. So from here you will get a kilogram, here you will put kilogram, and then the temperature here is Kelvin, so here you have per Kelvin as well. So now because this one is down here, so you can slash out the mole as well. So you will end up with the unit of meter square per second as your speed of this value should be 1.8583 times 10 to the power of 6. Therefore, you should get 1.3632 times 10 to the power of 3, and the unit shall be meter square per second. So this is the final answer for the 5th question. Let's move on to question number 6. What is the average translational kinetic energy RMS of 8 mole of gas molecule at 227 degrees Celsius? The formula for the average translational kinetic energy RMS is equivalent to KE RMS is equivalent to 3/2 nRT. So if you can see, this nRT is actually from the gas law, the ideal gas law. So your R should be equivalent to 8.3145 joule per mole per Kelvin. So therefore, here your N should be in mole and your T should always be in Kelvin, so that it matches your gas constant. Right? So if we look upon the question here, the temperature given to you is in degrees Celsius. So 227 degrees Celsius, you want to convert to Kelvin, you need to plus 273. Therefore, you will get 500 Kelvin. So now what we are going to do is we are going to just plug in the value. So given in the question, 8 mole of gas, so here will be 8 mole. Your R is the gas constant, 8.3145 joule per mole per Kelvin, and then your temperature is 500 Kelvin. So now we are going to slash out whatever that we can. So here is small and here is small, leaving you with the unit of joule. Therefore, it's equivalent to 3 over 2 times 8 times 8.3145 times 500. So this one have joule for the unit. So you will get 4.9887 times 10 to the power of 4 joule. So this is the final answer for the sixth question. Let's move on to question number 7. Determine the average translational kinetic energy of oxygen molecule at STP, given that the volume of the confined container and the Boltzmann constant are 2 liter and 1.3807 times 10 to the power of negative 23 joule per Kelvin per molecule. So the first step for you to answer this question is you need to use the ideal gas law, because in the question it states that it is at STP. So PV equivalent to nRT. And then at STP, the P is equivalent to 1 and the volume is given in the question, which is 2 liter. So 2 and the N is what you are going to find, and the gas constant is 0.0821, whereby the temperature at STP is 273. Therefore, from here we can get your N is equivalent to 2 divided by 2.2413 times 10 to the power of 1. Therefore, your N is equivalent to 8.9234 times 10 to the power of negative 2. If you look again at the question, you were given the Boltzmann constant, and in the Boltzmann constant, you need to have the number of molecules. So what we are going to do now is we are going to use the number of mole that we have calculated just now to find the number of molecule. So N times the Avogadro number, you will get the number of molecules. Therefore, your N is 8.9234 times 10 to the power of negative 2 times the Avogadro number, which is 6.0221 times 10 to the power of 23. So you will get 5.3738 times 10 to the power of 22 molecules of oxygen. Alright, so from here then only we can calculate the translational kinetic energy. Alright, so the formula for the translational kinetic energy, KE RMS, is equivalent to 3 over 2 nRT. Or we can also write it as 3 over 2 the number of molecule times the Boltzmann constant times the temperature. So this formula is more suitable to be used in this question. So now what we are going to do is we are going to plug in the value. KE RMS is equivalent to 3 over 2 N Boltzmann constant times temperature. So 3 over 2, your N is equivalent to 5.3738 times 10 to the power of 22 molecules. And then the Boltzmann constant given to you in the question, 1.3807 times 10 to the power of negative 23, and the temperature in Kelvin. So this one is joule per Kelvin per molecule, and the temperature in Kelvin at STP is 273 Kelvin. So now what we're going to do is we need to look at the unit. So we have molecule here and here, and then the temperature is in Kelvin, so leaving you with the unit of joule. So basically you just need to press your calculator and you will get 3.0383 times 10 to the power of 2 joule. So this is the final answer for the 7th question. Question number 8. Calculate the viscosity of methane at 60 degrees Celsius using the Sutherland's formula. According to the Sutherland's formula, the viscosity is equivalent to the reference viscosity times A over B times the temperature in Kelvin and divided by the reference temperature to the power of 3 over 2. So let's see what are the information given to you in the question. So you were asked to find the viscosity of methane and the temperature is 60 degrees Celsius. So from here we need to refer to our table. Alright, so according to the question, we shall be looking at methane and the temperature is 60 degrees Celsius and the nearest to 60 is 50 degrees Celsius. Therefore, we are going to look at this value and also the Sutherland constant will be 169. Alright, now we are going to calculate the viscosity is equivalent to the viscosity note, which is the reference viscosity. So the reference viscosity, we look upon the nearest temperature. So the nearest temperature is 50 degrees Celsius and we are going to look at methane. So this will be the value. So equivalent to 0.0120 and then times A over B and then the temperature. So the reference temperature, which is the T note, is equivalent to 50 degrees Celsius because what we are going to use now is 50. So 50 times 273 and then the actual temperature is 60 degrees Celsius. So 60 plus 273. So all these things you need to do to the power of 3 over 2. So now the viscosity is equivalent to 0.0120 times A over B. I'm just going to leave it as is like that first. So times 333 divided by 323 to the power of 3 over 2. Right now, what is A and B? So A is equivalent to 0.555 T naught plus C and B is equivalent to 0.555 T plus C. Alright, so your T is equivalent to 333 and your T note, your reference is 323. So if you look at the formula here, this one is the same, so you can slash out the C and this one is the same as well. So in other words, we can also write it as the viscosity is equivalent to 0.0120 times 323, which is the T note, and then divided by the T 333 times 333 divided by 323 to the power of 3 over 2. Okay, so from here you will get your viscosity should be equivalent to 1.2184 times 10 to the power of negative 2. So this is the final answer for your question number 8. So when you find the viscosity, the unit should be Cp, which you can find in here. Alright, we have come to the end of this week's video. If you feel that this video is beneficial for you, please give it a thumbs up and I'll see you again next week. So take care and be good. Goodbye.